So last class, we defined permutations. And that was this symbol P sub nk, and that was n factorial divided by n minus k factorial. So that's permutations and combinations. And combinations looked like this, C sub nk. And it looks almost the same, only it has an extra term in the denominator. So these are permutations, these are combinations. Does anybody have a question or comment about these definitions? We'll compute a couple. The point we tried to make is what these allow us to do is they allow us to count certain things. So what this means is if I have n total objects and I want to know how many different ways I can arrange k of them. Now, the permutations tell us that order matters in our arrangement, that if two guys have different orders, they mean the same, or they represent the same thing, where the combination means if the orders are different, that's okay as long as the elements are the same. So order is not important in a combination. So let's just do a couple of these real quick. By the way, there's a slight typo in the homework. I guess So for example, P of 12 sub 5, this is, what does this mean? This equals the number of permutations of 12 objects, whatever those objects are, taken 5 at a time. And so what does that equal to? It's equal to 12 factorial over 12 minus 5 factorial, which is 12 factorial over 7 factorial. And this simplifies to 12. Well, let's just write it all out for the first example, because our brains are probably fried. So this is, what is this by definition? This is 12 times 11 times 10 times 9 all the way down to 3, 2, 1. And then this is 7 times 6 times 5 all the way down to 3 times 2 times 1. And of course, a lot of these are what we say common factors. And so we can say bye-bye, bye-bye, bye-bye. And then of course, these guys all have partners upstairs. So this would simplify to 12 times 11 times 10 times 9 times 8. Which if I go to a calculator is 95,040. So that's a lot of different ways. Again, so imagine think about it this way. What does this represent? Let's think of like a real, put this in some context. So for example, let's think about something that there's 12 of. Say there's 12 months in a year. If I wanted to pick 5 months, how many different ways can I pick 5 of the 12 months and list them? 95,040 ways. It's a lot of different ways, right? Now, when we say that this is a permutation, that means order matters. So if I were to choose, say, March and December, then March and December is different than December than March. Do we understand that? Order versus non-order. Hopefully it makes sense. Okay. Now, what about the combinations? Well, we can do combination 2 of 12 and 5. So the number of combinations of 12 objects taken 5 at a time. So this is equal to, by definition, 12 not by definition, by the counting rules, 12 factorial over 12 minus 5 factorial times 5 factorial. And this simplifies to 12 factorial divided by 7 factorial times 5 factorial. And there's lots of different ways you can think about how to determine this number. You could go to a calculator if you want. The first thing I'll do is I'll write this as 12 times 11 times 10 times 9, that's a 10, times 8 upstairs. And then all that's left is the 5 factorial downstairs. So the 7 factorial downstairs can cancel out the 1 through 7 upstairs because it's all multiplication. And then if you wanted, you could say, okay, this is 12 times 11 times 10 times 9 times 8. And then this is over 5 times 4 times 3 times 2. And then you could start thinking about how you'd like to simplify. For example, 4 and 3 is 12, so these cancel. 5 and 2 are 10, so that cancels. And so you're left with 11 times 9 times 8. Which is 792. Well, okay, just think about it. What is 2 times 3? I'm sorry, excuse me. What is 4 times 3? 12. So that gets rid of this 12. And then 5 times 2 is 10. So you don't have to do it this way. I mean, another way to do it is you could just go to Google and say, what is 12? Choose 5, and Google will tell you that it's 792, even if you don't spell choose correctly. So just for you guys playing at home, let me show you what I'm talking about. I literally typed this in the computer. The computer, and well, you don't see it, but the one I see in front of me, I typed this, 12 choose 5. I didn't even spell choose correctly, and it says 792. So the answer is 792, whether we do it the long way using our own arithmetic or if we use a calculator. I would encourage that you know how to do it both ways, because when you're just trying to solve problems like this, then the calculator is the most efficient way. But when you're trying to solve new problems, and you might be looking for patterns or trying to understand what's happening behind the scenes, it's often best to write things out, because then you see really the hidden pattern behind everything. Does anybody have a question about this? All right, so the first I would argue that the first 5 problems on the test are straightforward. They're just these things. Oh, not the test, the homework. Problem 6 is a little tricky. I don't want to give it away. And I caution you, if you want to learn anything, don't just Google it. That is not learning. Googling the probability of getting 4 kings when you draw 5 cards. Googling that is not learning. Well, I take that back. If you Google it and then understand how to get the solution, then it's learning. But if you just write the answer down, you're not learning anything. You wasted your time. Because I probably won't grade problem 6 anyhow. If you've noticed, how do I grade your homework? I randomly select 2 problems. That's all I've been doing. I'm grading 2 random problems on every assignment. I can't grade them all. It would take forever. And plus, we've done most of the problems anyhow. So it's not like you don't know the solutions to these things. So problem 6 is tricky. Problem 7 is a little tricky. And problem 8 is a little tricky as well. I will treat problems 6, 7, and 8 as extra credit for those who actually give a detailed solution. Does that make sense? So again, I'm not going to grade 6, 7, or 8 other than it's extra credit for anybody who wants it. Fair? Let's give you some hints though about these problems. And because I think someone did ask, but I don't want to give it away because that's not, there's no fun when the answer is given away right away. So let me remind you of this. So problems 6, 7, and 8 on homework. What is this, homework 6? These are extra credit only. So you don't have to do them if you don't want to.
Grady.
Yes.
When I'm looking at homework now, I only got problems 1, 2, and 3. Don't show 6, 7, 8.
Are you looking at the second page? There's 2 pages. Are you looking at homework 6?
I got you now. I see it now. I didn't scroll down all the way.
All right, you got it. Very good.
Yeah.
Scroll, man. Scroll, Austin. Scroll. All right. So 6, again, we've done these poker problems. This one's a little trickier, but if you think about it, you might be able to make it happen. And again, you can Google it, but make sure you understand what you're doing. Don't just write down symbols and then tell me the answer. I want to know what the symbols represent. That's how you get points. Number 7. So we're going to sell 50 lottery tickets. And 2 are winners. No worries, no worries. Oh my God, I lost you, Samantha. Samantha, ain't no worries. It's no big deal. I feel you.
Thank you.
You're all good. Oh my God, you sound like a robot now. Playing a piano? Was it last class? No, this wasn't your class. Another class, someone was playing. They're giving us music. Now we will mute you all. If you need to speak, you can unmute your phone. My computer? I don't know what is happening. Our pets' heads are falling off. Do you know what movie that's from? Saying our pets' heads are falling off. I often figure you guys don't know anything anymore. You guys don't watch movies that are funny to me. That's what we said, Phil. It's like someone's playing the harmonica or something, or those things you played in like elementary school, elementary school music class. They'd have like a little bell, and you just like hit the. They'd give everyone a different size when you try to play a song. Did they do that when you guys were in school? Man? You don't know what I'm talking about? Or did you play those little weird flutes, the plastic flutes? What the hell are those called? The recorders or something? Oh, man. But then in my class, everybody started throwing them at each other, and then they took them off us.
Did you ever have the rhythm sticks?
Oh, yeah, that's what I'm, yeah. I
Bang the rhythm stick together?
think that's what I was trying to talk
They're
about.
like
man.
drumsticks.
Yeah.
They have like they're textured on the sides of them.
Oh, my God, what a time. What a time. Okay, so don't overthink this problem. You need the probability. So what is probability? You take the number of outcomes divided by, excuse me, the number of, okay, let's put it this way, the number of outcomes in a given event, and that event would be you winning both prizes, right? And you divide it by the total number of outcomes. So first off, you have to think, how many different outcomes are there? If they're selling 50 tickets, how many different, think about how many, which ones can you buy? Say we lined all the tickets up 1 through 50, you can buy the first and second, right? You can buy the first and third, the first and fourth, the first and fifth. Do you understand what I'm saying? So you have to think about all these different options. But this is really just a counting problem put in the context of a probability problem. So again, I would advise you to think about questions for you, how to solve. So think about all possible outcomes. Look, there's only one outcome, or how many outcomes are there when you win? Well, you would have to buy both tickets, right? How many outcomes are there where you don't win? Say that again.
48.
There's more than you. Okay, so don't think there's just 50 outcomes, right? So a good way to think about this is think about that there's 50 lottery tickets, and say for simplicity, there's 50 people. Okay, maybe not 50 people. That's a bad way of thinking about it. But okay, I still think the best way to attack it is to start by thinking, if we lay all 50 lottery tickets out, how can you buy them? Well, you can buy the first and the second. You can buy the first and the third. You can buy the first and the fourth, and the first all the way up to 50th. And then you could buy the second in the first. But that's the same thing as first and second. So right away, it's not permutations, it's now combinations. So what are you asking? How many different ways can you select 2 tickets from 50? And then you have to put that in how many different outcomes. So I don't want to give it away. But you should think about it in that context. And by the way, I think problem 6 is a little easier, but the way problem 6 is, I shouldn't say it's easier, but if you do problem 6, which we've done plenty of examples similar to that, instead of picking 3 cards now, we're picking 5. But if you do problem 6 correctly and you realize what the numerator and the denominator is, then it'll help you with number 7. Does anybody have a question specifically about the problem? I don't want to give it away. At least I'd like to give some of you a chance to solve it on your own before telling you all the fun of it. Another way to think about this problem is, and this is another hint I'll give you, and that is try to simplify first. What if there's only one winner? For example, what is your probability if there's only one winner? So this is another sort of problem-solving strategy. The problem we ask you to solve is what's the probability you win both prizes? But it might be easier if you first ask yourself, what's the probability that you win one prize if there's only one prize? So I'll let you guys think about this problem. Now we'll spend a little more time on 8. So, because it helps motivate one of our next topics. So again, I know that I didn't say anything about 6, but we've done plenty like 6. It's just a little more involved because it's 5 cards instead of the 3 that we've done. If you want to tack 7, these are my hints. And if you want to, you know, I'd be happy to answer any other questions. You want to email me, I'd be happy to give you more hints. But I do want to give people a chance to solve it if they're interested in that. And then problem 8 is an interesting problem too, because we're trying to think about if a game is fair. So this is going to sort of lead us into one of our next topics. Is something fair? So for example, are lotteries fair? Are casino games fair? How do we sort of quantify how fair a game is? How does a casino know how much to charge certain games and how games should be played so that they don't lose money? How do they know that? They don't lose money. I mean, I guess technically they're losing money now because the Roni won't let anybody go to Vegas, but in general, they don't lose money if the doors are open. How do they guarantee that? So let's look at number 8. So number 8 says, here's a game. The player rolls 3 dice. What is a win? A win, if the sum is 7, and you double your money. You lose otherwise. And so the first thing we ask is, what's the probability of winning? And then I ask, do you think the game is fair? Why or why not? So it turns out that you can answer this. Well, the probability of winning is straightforward. I mean, how many times can you roll a 7 with 3 dice? How many total outcomes are there? Well, the counting principle tells us that there are 6 for the first dice, times 6 for the second dice, which is 36, times 6 for the third dice. So what are the total number of outcomes? Well, that's 6 times 6 times 6, or 6 cubed, which is 216. So there's 216 total outcomes. How many of those outcomes, this is one way to solve it at least, how many of those outcomes are winners? You need to think about how many different ways can you sum up to 7. So you need the sum of 3 numbers to equal 7, right? For example, 1, 1, and 5 works, right? 1, 5, and 1 works. So you need to think about all these different options. There's a cute, quick way to count them all, or you can do it the long, hard way and write them all out. Does anybody have a question about this? So it was pretty easy. I don't want to say easy, but there was a simple pattern when we just did 2 dice. It was pretty straightforward to write out all the outcomes. But it's not maybe so obvious if we have 3 dice. Can you get to it? So there's not much more to say about this as far as the total probability part. Now, another way to think about this, by the way, is instead of thinking about total outcomes, you could think about it another way I showed you. Is you can, and this will lead into what we're going to do soon as well. Think about win and loss as a success. If you win, yay, lose, nay. How many, so you can think about it that way. So each roll, instead of thinking about the roll as, oh, okay, a number, think about it as yes or no. So there's a couple ways you could think about this. And I'll let you do that if you want. And again, these are all extra credit. And another way to think about this, by the way, is that you could use permutations and combinations to help answer this. All right, any questions? So let's write that down. One way to answer the probability or I shouldn't say write out, I'll use the magic word, is to count. I mean, I guess you could write them all out, but that would take forever. Is to count the number of winning scenarios and divide by 216, because that's the total number of scenarios. So again, another way to do this is do the problem instead of 3 dice. Think about the problem with 2 dice and see if you can see patterns, and then maybe allow those patterns to help you for the 3 dice. And then a real cool thing is, what if you increase the number of dice? Maybe you roll 10 dice, 20. Can you find patterns? Again, I'm just trying to intrigue you to think about gambling and math, because that's always fun. And then if you learn this stuff, then you could trick your friends and make money off it. What's wrong with that? And if you don't want to trick your friends, then you could just go set your own little casino up in the back of some restaurant and make money, right? Till the law comes for you. I kid, of course. Or no, I don't. Okay, so The last thing I'll talk about, which again is important coming up, is the game fair? So what I'm asking you, or trying to stoke your imagination, and first you have to even ask, what should fair even mean? Questions you might ask: do you expect to win or lose? Now, you might say, no, I don't expect to win, because you're going to say you're more likely not to roll 7 than a 7. And so say you bet $1 and then you lost $1, right? But you're not thinking about the bigger picture if that's all you think about. Suppose you have $100 in you, or on you, and you want to bet $1 at a time. So you might not win every bet, but don't forget you're doubling your money if you do win. So if you bet $5 and you win, now you have $10. Does that make sense? So you think about these things. These are sort of questions that hopefully spark some curiosity, and maybe they don't. I don't know. I'm hoping that they do. But I'm not going to be a fool. And again, I'm not expecting that all of you care about doing this. I just hope some of you do, because it's fun. All right. Okay. All right, time for some new stuff. And some of these ideas from these problems will be put into official context. At least that's the idea. Let's count to 10, see if anybody wants to say. I'm really cold in here. This class is like, I feel like I'm going to get pneumonia. I don't think that's going to matter. Was it? Yeah, maybe. You do whatever you want. I won't snitch on you. I found out when I listened to this new 21 Savage album that a snitch and a rat are two different things. Can you believe this? Then I heard some other numbskull rapper, I think I call him a knucklehead, but he said, this didn't make any damn sense. He said, talking about a girl, and he said, I went, what did he use? He said, I went Stevie Wonder, she can't see me. And I said, well, that doesn't make any damn sense. Stevie Wonder is not invincible. He is blind, which means he can't see, right? Do you understand what I'm saying? The logic here is very flawed by this. I forget who said this. I don't know if this was this 21 Savage or whoever the hell it is. Maybe someone else. I don't know. I got to stop listening to this new rap. It's driving my head insane. Did you listen to this 21 Savage album yet? I did. Good old. I think it's like, I don't know. Music's funny. Anyhow, back to math. How do we get on music? All right. Fun times. Okay, so we're going to move on. All right, new stuff now. We'll write it real big. New stuff coming up. Woo! So, now that we have some tools, we can make things a little more precise. So our first new topic is what we call probability distribution. So what we want to do is we want to think about if we, okay, so one of the things we spend a lot of time on is studying these examples of flipping coins and rolling dice. And you've heard me say on numerous occasions that the reason these are important is because they can be generalized, or that they are simplified versions of maybe more important things, like understanding when, things like, will a loan be paid off, or will, again, I've used these examples over and over again, but it's important to keep this in context. But what we need to do, if we're going to believe me when I say that we can use modeling coin flips as a way to think about if a medicine will either work or not work, things like that. Heads, it works. Tails, it doesn't work. Or heads, it's the person who takes out the loan pays it back in full. Tails, they don't. That kind of stuff. If we want to find a way to transition so that we can take the structure and idea of these things and actually apply them to maybe more sophisticated real world scenarios, we need a way of doing that. We need an appropriate language. We need an appropriate science. And so what we're going to do is we're going to start doing that sort of transition right now. So that's sort of what we want to do. So we need some new words, and some of these are going to be scary. And so I hope that you stick with me. And don't get too afraid. All right, so the first thing we need is what's called a random variable. And here we go. So a random variable is a function. So you guys are familiar with functions, but this is a kind of a new type of function that maybe you're not so familiar with. It is a function from a sample space to another set. So now we're using some words that you've probably have had defined in a class before, most likely a math class, but you were never given much thought to it. When you study in an algebra class, you study functions, and one of the things you learn about a function is they have this thing what you call a domain. That was like the input of the function, and then it had an output. And you might remember words like domain and range. And typically in an algebra class, the functions you studied, you gave it a number and you put it into some formula and it spits out a new number. Most of you are familiar with that. But in general, function can be much more abstract than that. A function is a rule that associates one element in some set with elements in another set, or excuse me, one element in another set. So it's a little more abstract than that. And it doesn't always have to have some simple, I don't say simple, some algebraic formula that you're familiar with. It can be a lot more abstract than that. The word set in mathematics, you could just think of that as a collection of objects, anything. You're familiar with certain sets of numbers, the integers, the real numbers. You're familiar, hey, I know these are the even numbers, these are the odd numbers. I have a collection of golf balls at home. I have a set. So you could, in math, we call any collection of things a set. So the best thing we can do before anything else is to think about a specific example. So let's go right to our original example of tossing coins. So consider tossing a coin, let's say 3 times. So we know there are 2 to the power 3, which is 8 outcomes. In the sample space. So we can even list them. Let's list them for fun. So there's heads, heads, heads. That's one option. We can have the option heads, heads, tails. We can have the option heads, tails, heads. Or we can have the option tails, heads, heads. That's the first 4. We can also have tails, 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 and then you can have tails, heads. Excuse me. Let me keep the symmetry up to make it a little easier. You can have tails, tails, heads. You can have tails, heads, tails, or you can have heads, tails, tails. So this is going to be scary. A random variable is a function where the input is one of these 8 options. So this is a little different than you're thinking about where you'd say f of 3, like you might remember from an algebra class. So what we're going to do is let x, capital X, equal the number of, say, heads. That is a random variable. Now, let's put it, and we typically don't do this in probability and statistics, but it might be nice for you to see it once to like make a connection. Let's see the values. Let's see why it's a function. So how did you typically write functions? You would say, normally you guys are used to calling a function f or something, or g, right? And you're used to like f parenthesis g. You know, many of you guys are used to stuff like this, right? Equals like 3x squared minus 6. You've seen stuff like this before. But now x is actually the name of our random variable. So it's the name of the function. So this gets kind of scary. So let's think about this. The inputs are the sample space. So for example, X has an input. What's the first input? It's heads, heads, heads. So what does that equal to? Well, how many heads do you see? 3, right? And then you have X of, say, heads, heads, tails. Well, there's 2 heads here. Or you have X of heads, tails, heads, and then there's 2 heads there. Or you have X of tails, heads, heads, and there are 2 heads there. We can also do the other ones. The other ones we had, okay, what if we had X evaluated at, well, I wrote that backwards. Did I, not backwards, did I skip my, no, that's good. So the next thing we could do is we can do the other 4 scenarios. So here, let's do the tails, tails, tails. There's 0 heads there. Then there's tails, tails, heads. There's 1 head here. Then there's tails, heads, tails. Once again, 1 head. And then, of course, the last one was heads, tail, tail. Which, of course, there was, once again, 1 head. Now you might say, why are we doing this? Well, it turns out that the notation becomes a little easier if we do it this way. Now, it's not going to be easier at first. You're just learning it. You're going to be confused as hell. But once you understand what these symbols mean, this is a much more effective way of studying probabilities. So let's look at this. Look at these numbers we have. How many times do you get 3 heads? Well, that happens once out of the 8. How many times do you get 2 heads? Well, that happens 3 out of the 8 times. How many times do we get 1 head? That happens 3 out of the 8 times. So now when we want to talk about probabilities, it becomes a little more efficient to talk about the probability of a random variable. It's a much more efficient way, once you learn it, to do these probability questions than what we've been doing in the past. Again, the examples we've done in the past were only sort of easy for us to do it the long way that we were doing it because we could draw it out or we could recognize patterns. But in general, that's not going to be the case. Again, do you want to write the sample space out of flipping a coin 47 times? I don't think you do. Okay, so one of the things that helps us is it helps us to maybe write things and arrange things in tables so we can sort of see structure. So let's do that. So we can now recall our probabilities. And I can't spell. I hate this pen. It makes me look like I can't spell, though maybe I can't. Maybe it's because my hand's numb because it's so damn cold in here. So look how I'm going to write this now. What is the probability that I get? What is the probability I get 3 heads? Well, that's 1/8. What's the probability that I get 2 heads? That is 3/8. What's the probability that I get 1 head? That's 3/8. And what's the probability that I get 0 heads? Well, that is 1/8. Now, of course, to the amateur, and that's what you are, this looks like a bunch of symbols. It looks confusing. But it saves us from having to write all kinds of words out all the time. Did you notice how sloppy it was when we were doing those problems the last couple of weeks? I'm just putting P in parentheses and I'm writing words in there and there's no consistency, there's no convention. Well, now we have some convention, we have some consistency. So I know this is frightening you right now, and how do I know that? Because I sympathize and empathize. I had no idea what I was doing when I first learned this as well. It was scary. That's just what it is. I got my buddy Obo, he says that. It is what it is, man. That's what he says. It is what it is. You wouldn't believe. Ob actually looked like you yesterday. I should show you a picture. He had a camo outfit on with a headband. Now, he has tattoos on his face, so that's something you don't have. And most people are like, you hang out with someone with tattoos on your face? I said, yes, that's my buddy Ob. Tattoos. I'll have to bring him in here one day. He's a big gambler. All right, so what does this mean? So P of X equals, say, 2 means the probability the random variable X equals 2. That is, in shorter terms, that is the probability that we flip 2 heads. It's hard in your position to appreciate why we want to use symbols, because, you know, from your position, it's ironic in the big circle of life how originally math and science was done by writing everything out in words. You know, if you go back to textbooks and how we did math a couple hundred years ago, there were no algebraic symbols. They hadn't been invented yet. Everything was done using words. And then, fortunately, lots of different cultures realized that symbols were useful. And so we developed this sort of language of symbols like algebra and calculus. And it helps it. It makes us solve more complicated problems more efficient. And then it's ironic because when you guys were kids in school, you would learn a technique in math, and then you would do the basic, what we call elementary problems, and then they would put it in the context of like a word problem, right? They would write it all out in English, like a story problem, and you'd have heart failure because you couldn't translate the English to the symbols, right? And everybody in math class in middle school says the word problems are the hardest, right? But now that's why. So we don't want to have to write, I shouldn't say that's why, but it's coming full circle. So the idea is you don't want to have to write all these words. You don't want to have to repeat yourself over and over again when context is clear. So if we say we're going to make a definition that X is a random variable, then it allows us to have this much cleaner and concise notation, amongst other things. That's not the only benefit to this. Now, of course, it's hard when you're the amateur because you have to, this just looks like symbols. You're like parentheses, there's 2 equal signs. What the hell's happening, right? That's what you're thinking. And I understand that because I've been there before. But you just gotta trust me that it is a much more useful way of doing this. Another way to see this, and we'll do this on the next page, is to visualize it slightly differently. Does anybody have a question about this?
So you're trying to do it like quickly, and you're not going to write them all out to be able to figure out that you had 3 heads and you had 2 heads. And
Okay, right. So it becomes more efficient. And not to cut you off, but maybe this will answer your question. And then if not, tell me what you want to say. If I write at the beginning of the problem that X equals the number of heads, then I don't have to write it down ever again, right? Why waste all that space? I mean, think of, and it's not a laziness thing. It's a convention thing. And it's also, it allows us to, you know, moving forward when you do certain things. Now you might say, I don't plan on doing those things, which is fine. But we still have to teach you the language in which the professionals use. Does that make sense? Yeah, there's nothing wrong with me writing P parenthesis, I roll 3 heads, or excuse me, I flip 3 heads. But that takes up space, and it's not, again, it turns out things you want to do later, it's not conducive to using words. It's conducive to using more efficient symbols. Does that make sense?
yeah, I wasn't really sure like how else would you go about doing like, the problem to be able to get you have x equals 3 or x equals 2, other than writing them out and then like transferring it into this?
Yeah, okay, you're going to see. That's a good question. So the question was, how else would you do it? I think, right? So, I think what you'll see is that what we're going to be doing, it's this. If it doesn't make sense to use this now, what we do soon enough, you'll say, okay, I see how this would be really hard to use with words if we didn't have this notation. Does that make any sense? Okay, so, and this might be insightful too, what we do next. We can also draw this sort of like a table. So alternatively, we can make a table. So what do I mean by a table? Well, let's say X, which equals the number of heads. So what are my options for number of heads? Well, I can have 0, right? 1, 2, or 3. And then I can compute the probability. Which is P of X. And that would be, we already found this. This is 1/8, this is 3/8, 3/8, and 1/8. So that's another way to visualize this sort of function X and its probability. All right, so we call this has a name. This is an example of a probability distribution. Why do we call this a probability distribution? Well, it's showing us how the probabilities are distributed. 3 of the 8 are here. 3 of the 8 are there. 1 of the 8 are this. The other of the 8 is that. It's showing us how the probabilities are distributed. What's more likely, getting 3 heads or 1 head? What's interesting to note is, as you would expect, these numbers add up to 1 because we know the sum of all the probabilities has to be 1. Does anybody have a comment or a question?
So I think my question wasn't really answered exactly.
All right, well, yeah, so say it again. Yeah.
So say if you were to restart the problem all over without knowing how many heads were in
Okay.
one flip option, how many tails were in this flip option, and you're just to look at the problem again and think like, how am I supposed to start this? But you want to use it in simple form, that like x equals 3 or x equals 2 in that sense, and then you get like your fractions at that point. Like, how do you go from just looking at the problem to I'm going to use the simple form?
How would you mean? How do I get the fractions without writing it out? Is that what you're
Yeah,
asking?
like, if you're saying like if you were to do it without writing it out, and you're trying to just be like,
Okay. So the question that I think that you're asking is, if I go back to when we did this example, if I don't write these out, how do I get the numbers? Okay, well, that's what we're going to build to. So once that's a good question. So it turns out that there is a very, very nice way of doing this. I mean, we sort of alluded to it already. I mean, think about this. If I'm going to flip a coin 3 times, say I want to know how do I get 3 heads. Well, that means how do I get a head? What's the probability of a head?
1 and 2.
Right. So, okay, so head is what? Half times half times half, or 1/8. Right? Now, what about 2 heads and a tail? Well, I can get 2 heads and a tail 3 ways. So yes, I don't, and we're going to show you that in a second. So like what I'm saying by this is I get 2 heads and a tail this way, or this way. So it's what is this? This is going to be 1/8, and this is 1/8, and this is 1/8, but how many are there? There's 3 times 1/8. Does that make sense?
Yeah.
So there's actually a pattern there. And this is an example. Coin flips are an example of a very, very important and useful distribution, which is going to be, maybe you've heard of it before. It's called the binomial distribution. Get it? Binomial. So 2, bi. Right? And there's 2 options, heads, tails, success, failure. And so there's a real clean way of characterizing that. And we're going to get to that. Maybe not today, but on Wednesday. So it turns out you can see there's a formula. I didn't write it out, but there's clearly a formula for P equals, or P of X equals, say, K. There's a formula for it. And it turns out the thing is, what we need are those combinations, because the combinations tell us, think about this. The combinations, here's a good insight too, if you want to think about this. Think of this way. Think of, if I want to know how many different ways can I choose 2 guys from 3, what is this equal to? So if I have 3 objects, say a coin flip result, how many different ways can I pick 2 from it? Well, what is this? This is 3 factorial over 1 factorial times 2 factorial, which is, if you just write it out, is 3. That's not a coincidence. If I flipped the coin 5 times and I wanted to know how many different ways I can get 2 heads, it would be 5 choose 2. Because there's 5 choices and I want to know when 2 of them or something. So there is a connection here. So, and again, if I'm not answering your question correctly, I think,
I'm seeing it more now.
does that make sense?
Yeah.
So I think the question was, how would I know what this is without writing it out? And when you say writing it out, I believe you're implying writing out the sample space. And what I'm telling you is there is a pattern, and it turns out the combinations are going to be the shortcut. Okay. Very good. So what makes a probability distribution? So what is a probability distribution? It is a function. So we have the word function again. That gives the probabilities of different outcomes. Now, so this is going to look very overwhelming, but this is one way you can do it. So what we might do is we might define f of, say, k, and what is it equal to? It's equal to the probability that x equals k. So you know, what is the probability that f of 0? Well, that is the probability that we get 0 heads, which we found to be 1/8. What is f of, say, 2? That's the probability that we get 2 heads, which we found to be 3/8, etc. So this is, again, very overwhelming when you first learn it. The symbols are, it's like symbol overload. I get that. I wish there was a better way for me to do it. So again, the symbols are overwhelming. I wish there was a better way of doing it, but there's not. And what gets worse is on Wednesday, we have to define what's called the mean of a distribution, and that definition is symbolically overwhelming. And the best thing I can tell you is don't get discouraged. The symbols, yeah, they are kind of ugh, but you can get through it. I know you can, because I did. And anytime you think you can't do it, all right. Any questions, comments? So work on that homework. Please try to submit it tonight. The extra credit, I don't care when you submit it, but you should try to do it soon. And then I'm going to start working on some of this stuff too. And by the way, we got to get you guys some points. I got to give you a nice little quiz or something, like a simple little quiz on the Canvas machine. All right, guys, thank you very much. I will see you Wednesday. Take care.